Hello, I'm Meghamala, working as Assistant Professor from Institute of Aeronautical Engineering. And today I'm going to talk about bidirectional gates. So let's see what are the bidirectional gates. In the previous classes, we have discussed what are the gates and different types of gates we have discussed. And regarding switches also we have discussed in the previous cases. So here, regarding to this bidirectional case, as we know that Verilog is it has 26 sets of primitives, gate primitives. In the Verilog library, we have 26 sets of gate primitives. So here, basically, Verilog has a set of primitives for bidirectional switches as well. So here, this Verilog, the Verilog library, it not only have a gate primitives, but also the Verilog has 26 sets of gate primitives along with the bidirectional switches. So they connect here. They connect the nets on either side when on and is isolated them when off. So here, when the switching mechanism comes, we say that they connect. That means the switches can be connected with respect to the nets. Nets are nothing but here in the Verilog terminology, the nets are nothing but the variables. Okay, so here they connect to the variables or else to the net on either side of the switches. That means what? If they are connected to one end, then the switch goes to on, and if it is not, and then it goes to off. Okay, so the signal flow can be in either direction. So here the signal flow can be in unidirectional or as well as the bidirectional. As I said the switches can be unidirectional and or the both bidirectional. So here the signal flow, it could be either in the unidirectional, that means the one-way direction from the input to the output, and also it could be of both the directions, that is bidirectional. There are 6 types of bidirectional gates. So here the bidirectional gates are of 6 types. Tran, R-Tran. We have discussed what is the R-Tran. R-Tran is a resistance transistor. The second one is Tran if 1, R-Tran if 1, the resistive switches, Tran if 0, and third one is R-Tran if 0. So here, these are the few combinations, 6 types of bidirectional gates. That means what? Here, the output can be the flow of the current, it could be of both the sides, from input to the output and as well from the output to the input. So here these are the 6 combinational switches, bidirectional switches. R represent the resistive switch. Okay, so here R represent the resistive switch. In the yesterday's class, we have discussed the resistive switches. Resistive switches are nothing but the similar to the normal switches, that is P transistor. If it is a P transistor, we represent the resistive P transistor as Rp-Tran. Okay, and if it is a N transistor, we represent the resistive switch as Rn-Trans. Okay, but here the mechanism comes the same. When it comes to the R-Tran with respect to the normal transistor, the mechanism comes with the same fashion. That means what? When the control signal is 1, regarding with N transistor, NMOS, that is NMOS, when the control signal is 1, what happens? The switch goes to on. Okay, and if control signal is 0, then the switch goes to off. Whereas when it comes to PMOS, P transistor, when C is equals to 1, the switch goes to off. Okay, when the control signal is 1, then the switch goes to off. And when the control signal is 0, then the switch goes to on. So these two are P transistor and N transistor and P transistor. That is PMOS and NMOS. Mechanism wise, they both are contrast to each other, quite opposite to each other. The switching mechanism of these two transistors, PMOS transistor and as well as the NMOS transistor, are quite opposite if based on the control signal. Okay, so here when it comes to the resistive switches, in the resistive switches as well, the representation of P transistor, that is PMOS, is we represent as RP MOS, and if it is NMOS, we represent as RNMOS. Okay, and if it is CMOS, we represent as RCMOS. The representation goes like this. So here in the bidirectional switch, as I said we have 6 types of bidirectional switch based on transistor and transif 1, transif 0, RTran, RTrans 1 and RTranif 0. Okay. So coming to RTran and Tran and RTran. So what are these Tran and RTran? So these are the bidirectional switches, or else the Tran gate is a bidirectional gate of 2 ports. So here Tran is a bidirectional gate of 2 port. When instantiated, it connects 2 ports directly. So here it is a bidirectional gate of 2 ports, right? So here when you are instantiating, what happens? It connects the 2 ports directly. Directly it connects the 2 ports. Thus the instantiation goes like this. Trans, S1 and S2. These are the 2 ports. Where the transistor here, this gate is connecting these 2 ports directly. So it connects the signals lines S1 and S2. So this transistor, it is connecting the signal lines S1 and S2 directly. Okay, that means what? Either line can be input, in-out or output. That means what? In the terminal list, when it comes to the instantiation of the Tran, okay, instantiation of the Tran is a bidirectional gate. When it comes to the connection, we are saying that this Tran can be connected to signal lines, okay, 2 signal lines S1 and S2 directly without any intervention of the other element. This transistor, this Tran gate, it can connect 2 signals directly. So here the connection, it could be the line, this signal line, it could be either input, output or in-out. Okay. So here in the instantiation, in the terminal list, this is how we will represent. And then RTran is nothing but the resistive counterpart of Tran. As I said we have 6 different types of gates, right? Bidirectional gates. So for each and every bidirectional, it can relate to the resistive gate, resistive bidirectional gate. As I said for PMOS, the resistive bidirectional gate would be RPMOS. For NMOS, resistive directional can be RNMOS. Okay. For CMOS, resistive bidirectional gate could be RCMOS. And for trans gate, the resistive bidirectional could be RTrans. Okay. And if 1, the resistive bidirectional could be RTran if 1. Like this. Okay. Then coming to Tranif 1 and RTranif 1. So as it is also one of the bidirectional gate, Tranif 1 is a bidirectional switch, turns on and off through control line. So based on the control line, this particular bidirectional gate Tranif 1, it could be either on or off, which is based on totally the control line. Okay, all the switches they follow the mechanism, or else they go switch on and off based on the control lines. Okay, when it comes to the basic PMOS transistor and as well as NMOS transistor, based on the control lines, the switching takes place. So likewise here in the Tranif 1 and Tranif 0, we are saying that it is a bidirectional gate and the switching takes place with respect to on and off based on the control line. Okay, so it is in the on state when the control state is in high state. That means what? This Tranif 1 is talking about the switching of on and off when the control signal is high, isn't it? When the C is high, 1 means high. When the control signal is high, we are saying that the switch goes to the Tranif goes to on condition. When the control state is low, okay, that means what? 0 represent low. When the control signal is low, then the switch goes to off state. Okay, so here the instantiation of the particular TRAN-if gates goes like this. TRAN-if 1 is a bidirectional gate followed with the terminal list. In the terminal list, we are representing the selection lines. So here we have two selection lines along with the control lines. So here the signal transitions. See here, C is a control line, isn't it? Based on this control line, only we can say whether the switch is on and off. So here C is a control line, and then if control line is 1, what happens? S1 and S2 are connected and the signal transmission taken either direction. So here, as S1 and S2 are the signal lines, okay, that means what? S1 and S2 are connected directly to each other. The gate, the transition gate, this TRAN-if gate 1 is nothing but it has a control line and as well as a two selection lines, and these two select signal. These two signal lines can be connected directly. Okay, and now the mechanism of switching goes like this. When the control signal is high, we are saying that the switch goes to on condition. That means what? Here the both signal lines S1 and S2 are connected to each other. When they are connected, then we are saying that it is in on state. Okay, then R TRAN-if 1 is a resistive. So the same mechanism goes with this R TRAN-if 1 similarly like the TRAN-if 1. So remember that TRAN-if is a bidirectional gate. Based on the control lines, it can switch on and switch off. So here in the instantiation, TRAN-if 1 is a name of a gate. It's a bidirectional gate in the terminal list. Okay, in the terminal list, as we are representing the terminals, input terminals, output terminals, and as well as the inner terminals, remember that output terminals are represented first and then goes with the input terminal. So in a similar way, here we have the signal lines S1 and S2 along with the control line. So when the control signal is 1, that is when the control signal is in high state, it means that the two signal lines can be connected to each other. When the two signal lines are connected to each other, S1 and S2, that means what? The switches goes to the on condition. Okay, and the signal flow can be of either direction, from the right to left or else from the input to output or else from the output to input. As it is a bidirectional switch, the signal flow can be of in the both the directions. So here, our TRAN-if is a resistor counterpart of TRAN-if. It is instantiated in the identical manner. As I said you, when it comes to the TRAN-if 1 and R TRAN-if 1, they both are similar, but the only difference is it is a resistive switch. Okay, the only thing is it is a resistive switch, but the rest of the thing and the mechanism or else the switching thing is similarly with respect to the TRAN-if 1. So coming to TRAN-if 0. TRAN-if 0 and R TRAN-if 0. So this is one of the bidirectional gate where here the switching mechanism goes like this. So TRAN-if 0 and R TRAN-if 0 are again, these are the bidirectional switches. So here the switch is off if the control line is in high and on when the control line is in 0. So this TRAN-if 0 is similar like PMOS transistor. Remember, the TRAN-if 1 is similar to NMOS transistor, whereas TRAN-if 0 is similar to PMOS transistor, isn't it? In NMOS transistor or else in the TRAN-if 1, we have seen that when the control signal is 1, when the control signal is in high state, we say that the switch is in on condition. Okay, so similarly in TRAN-if 0, we are saying that the switch is in off when the control signal is high. When the control signal is high, the switch is in off. So this mechanism is similarly like the PMOS transistor. In the PMOS transistor as well, when the control signal is 1, what happens? The switches goes to off condition. And when the control signal is low, then switch goes to on state. So similarly, in TRAN-if 0, we are saying that the switch is off if the control signal is 1, that is high state. And when the control signal is low, then the switch goes to on condition. When the control signal is low, the switch goes to on condition. Similarly like PMOS transistors. So here, with the above instantiation, That is, if C is equals to 0, what happens? When C is equals to 0, S1 and S2 are connected and the signal's transition can be in the either direction. This is quite opposite to tran if 1. So here, tran if 0 and tran if 1, they are quite opposite to each other. And then if C is equals to 1, the switch is off and S1 and S2, they are isolated. Okay, when they are connected, that means when the switch is on, always remember that the two signal lines S1 and S2 are connected to each other. That means the switch is in the on state. When the switch is in off state, S1 is isolated with respect to S2. Okay, the isolation takes place when the switch is in off condition. So here in the tran if 0, we are saying that the switch is in off condition when the control signal is 1. Okay, but here it is quite contrast with the tran if 1. They are opposite to each other. So this is the instantiation. Here we have tran if 0. In the terminal list, we have the signal lines S1 and S2 and the control signals, control input. And coming to the instantiation with strengths and delays. So we know about the delays. In the previous module, different kinds of modeling styles. In the behavioral modeling or else in the gate level modeling, in the switch level right now we are in the switch level modeling and data flow modeling. In all these modeling styles, we have seen the delays. So delays are with respect to the time controlling elements. So delays are nothing but they deals with respect to the time control elements, isn't it? When you are having inputs A and B, with how much of delay the input A is reaching the output. This is what in terms of time constants will be knowing the delays. Okay. So here instantiation with strengths and delays. What are the strengths? Strengths are nothing but the signal with how much of delay. If the delay is maximum, the signal strength goes minimum. Okay, they are quite opposite to inversely proportional to each other. The strengths and delays are inversely proportional to each other. So here we'll see the propagation delays can specify for switch primitives on the same line as done with the gate primitives. So here when you compare the gate primitives and the switch primitives, we see the propagation delays. Okay, the propagation delays can be specified switch primitives on the same line as done with the gate primitives. So here there is no much difference that we can see when you compare the delays in the gates level and as well as the switch level. Okay, they both are one and the same. The mechanism goes with both modeling styles are one and the same, either with the gate level and also with the switch level. Now, as NMOS switch instantiated, how? The NMOS switch, we know the NMOS switch mechanism, right? The switching, when the control signal is 1, the switch goes to on state, and when it is 0, the switch goes to off state. Okay, so here NMOS is nothing but the keyword. This is a keyword and G1 is a gate. Okay, it is a name of the circuit, name of the module. And then in the terminal list, this is a terminal list. So in the terminal list, we will be representing the output, input and the control. So here, the instantiation of this NMOS gate has no delay associated with it. So here if you observe this particular instantiation, we see there is no delay. Okay, usually if you have any delays in the propagation, area, if you have any delays, usually we will represent the delays over here. Okay, with the keyword like delay. Usually we will represent it. Okay, when it comes to the behavioral modeling, we used to represent the delays in terms of ash 10. Ash A is equals to 10 like that, or else ash 10 is equals to B. Okay, that means what? The B input is propagating its signal with the 10 nanoseconds of delay. This is how we would we have represented in terms of the behavioral modeling style. But now as we are discussing in the switch level modeling, the delays here, as per this statement, we don't have any delays. So we are not representing any delays over here. For example, if you have any delay, that means what? If a signal is having propagating with some delays, then the instantiation goes like this. The instantiation of NMOS, here we have a delay, right? Delay 1 with respect to the gate, the circuit that the digital circuit that you are considering, the module and the terminal list. So here the signal is propagating with some delay. There is some delay in the signal propagation. So we need to represent that delay. So here I am representing the delay 1. Okay. So the delay 1 has a delay which is for the output to rise, fall and turn off. So here the delay could be in terms of, I said to you, the delays are in terms of time controlling devices, time controlling elements, right? So the delay, it could be either in rise time, fall time and what is turn off, okay, turn off time. So in these terms we can represent the delays. And then the instantiation of NMOS, and we have delay R. So that means what? With respect to rise time, fall time and turn off time. Okay, if you are observing any delays with respect to these times, with respect to rise time, fall time and delay time, then the representation or else then the instantiation of the delays with respect to the rise, fall and turn off times, this is how we will be representing. So the instantiation NMOS, here my delay, okay, I've seen some delay with respect to the rise time. We all know what is a rise time. 90% of increase, right? From 0 to 90% is nothing but the rise time, isn't it? And then it is a fall time is from 90% to 0% as well. This is the fall time, isn't it? So here the delay, I've seen it with respect to the rise time. So delay R, and as well have a delay in the fall time, delay F, and then gate and followed with the terminal list. Okay. So here delay R as a rise time for the output. So here in the output, I have found some delay. That delay I have got with respect to the rise time. So that is the case I am representing, or else the instantiation of the delay with respect to the rise, fall and turn off times could represent this fashion. So here delay F is for the fall time of the output. Usually we are representing the TR, TF and T off time, right? So here delay, if delay is with respect to rise time, this is how we will represent, and delay with respect to falls, this is how we represent, isn't it? And if it is off time, delay with respect to off, and this is how we are representing the delays with respect to the rise time, fall time and off time. So here the turn off time is 0. So the delay F is a fall time for the output. When the delay F is fall time for the output, then the turn off time will become 0. So here the instantiation with respect to the turn off time, how can we represent, or else how the delays can be represented with respect to turn off time is given like this. This is a NMOS, delay R rise time, fall time and as well as the turn off time. Okay, turn off time, and G for the gate, the terminal list, turn off time. This is turn off time. So here the delay F is a fall time. For the output, delay O is a time to turn off time. So here we are representing the turn off time as delay O. Okay, turn off time as delay O when the control goes from 0 to 1. So here when the control signal goes from 0, low to high, then what we are saying, the turn off time, the fall off time. The fall off time for the output delay would becomes turn off. Okay, is a turn off time. That means what? When the control signal is going from 0 to 1. So here the delay can be assigned to the unidirectional gate as well. So here this rise time, fall time and turn off time, these 3 times are not only meant for the bidirectional gates, but also they can use for the unidirectional gates as well. So here for the unidirectional gates, that means what? Here we have RCMOS. That means with respect to the resistive gates, Okay, resistive switches. So RCMOS switch, and with respect to the PMOS, RPMOS resistive, CMOS and RCMOS as well. Okay, in a similar way. How we are representing the delays with respect to the PMOS, NMOS, we can also represent the delays with respect to the CMOS and as well as the resistive switches. So, the bidirectional gates do not delay transmission. Their rise fall times are 0. So, here the bidirectional gates, switches, they do not delay the transmission. They do not delay the transmission either when they are rise, when they are fall and when they are the turn off times. Okay, but here all these are the switches, they do not transmission. Then that means what? If there is no delay in transmission, what happens if there is no delay? That means if delay is 0, obviously the rise time, fall time and turn off time, all the times will become 0, isn't it? If there is any delay, then the delays goes with respect to the rise time, fall time and turn off time. If in the transition, if there is no delay, then obviously the time, all the times with respect to the rise, fall and turn off times will become 0. And then they can have only turn on, turn off delay associated with them. Okay, in the bidirectional, they can have only turn on and turn off. So, the TRAN has no delay associated with it. So, here when it comes to the TRAN bidirectional gate, we are saying that it has no delay associated with it. So, here if the TRAN, with respect to the TRAN bidirectional gate, with respect to the TRAN, we don't have any delay. When there is no delay with respect to the TRAN bidirectional gate, then obviously the instantiation goes like this. TRAN out S1 S2. Simple. Okay. Now, when it comes to TRAN-if1, so here TRAN-if1, having TRAN-if1, the delay I have with respect to the rise time, fall time. Okay. So, here it represents the instantiation of the controlled bidirectional switch. So, here when the control signals changes from 0 to 1, when it is changes from 0 to 1, that means what? The switch turns on with the delay of rise time. That means what? Here, when the control signal, when the C is going from 0 to 1, what happens? Here we see, say there is some rise. So, this is nothing but the rise time. Isn't it? This is nothing but the rise time. And here, it is a fall time. So, when the control signal changes from 0 to 1, what happens? There is a rise in the signal. So, we represent there is a rise in the signal. So, there is how much of delay? That means representing the delay is with respect to the rise time. So, delay R, delay F, and delay F we see when it changes from 1 to 0. So, when it changes from 0 to 1, there is a delay of with respect to rise. And when it is changing the control signal, when it is changing from 1 to 0. So, this is 1 and this is 0. When it is changing from 1 to 0, we see there the delay with respect to the fall. Okay. So, the delay is with respect to the fall. That is what we have instantiated, and that this is with respect to the TRAN-if1. So, here in the TRAN-if1, we see the delay with respect to the rise time and delay with respect to the false time and the gate that you are considering, and this is a terminal list. Obviously, in the terminal list, you will see output, input and control lines. So, when the control lines when the control signal is from 0 to 1, obviously there is a rise in the signal. So, the delay goes with respect to the rise, DR, delay R. When the control signals, it drives from 1 to 0, then we see there is a fall. Okay, so there is a fall in the switch and the switch is turns off. Here the switch turns on, whereas here the switch turns off. So, this delay we represented with delay F. So, next is TRAN-if1, trans-if1. So, here we see the delay 0. So, it represents the instantiated with delay 0. Here we see some delays with respect to the rise and fall, and in this particular example, we see we are presenting it with delay 0. Okay, so the delay 0, it switches from delay 0 for the switch to turn on when the control signal is from 0 to 1. Obviously, when the control signal is from 0 to 1, what happens? The switch goes to on, isn't it? So with the same delay, for it to turn off when control signal changes from 1 to 0. So when it changes from 1 to 0, obviously the delay falls down. Okay, the delay will become less, that is 0 delay. So it changes from 1 to 0. So this is about the delay 0. And when the delay value is not specified, in some cases we don't specify. For example, tran. In tran, if there is no delay, obviously we will write out, in and in out, right? So when the delay value is not specified in the instantiation, the turn on turn off times are considered to be idle. For example, this only. So in tran bidirectional gate, if there is no delay, obviously there is no need to represent the instantiation. In the instantiation, there is no need to represent the delay. Why? Because here the delay is 0. There are no delays. So when there is no delay, what says that the turn on time, the T on and T off time are in the idle condition, idle state. The turn on and turn off are in the idle state. So when they are in the idle state, there is no need of representing delays. Why? Because the delay is 0. There is no delay, and so we don't represent delay in the instantiation. In the most general form for the instantiation, signal strengths and delay values can be combined. So here, in the most of the cases, when you are representing pertaining to the transistors, pertaining to the switches and gates, in the instantiation, we will be representing with respect to the signal strength and the delay values. Okay, so this topic is about the instantiation of the signal strengths and delay values, right? So here, most of the cases, if the delays are 0, there is no need to represent the delays. But in some cases, there is a possibility to represent the signal strength and as well as the delays. Okay, so here, coming to the example, here I have considered the NMOS transistor. So here, as I am considering the NMOS transistor, my keyword should goes with the NMOS. And then here, I have a signal strength, have a strength. Okay, I have a strength values as strong 1 and strong 0. So here in the instantiation part, I am representing, or else I am instantiating the things with respect to the strengths. Okay, these are my strengths and these are my delays. Okay, I am representing the strengths and delays, and this is a circuit that I am considering, and here is a terminal list. So in the terminal list, obviously have to represent the signals, isn't it? Signal levels S1 and S2 with respect to the control signal. Okay, so here, which means that, let's see, what is this strong 1 and strong 2? These two are the strengths, right? So it has a strength 0 and 1 when the low state, and the strength 1, a strong 1 when in the high state. So here, when it comes to the strengths of a signal, when the signal is in low, okay, so we represent the signal. If the signal is in low state, then we represent the strength of that particular signal is strength 0. When the signal is in high state, okay, then we represent the strength of that particular high state signal as strength 1. Okay, this is regarding the strength of the signal. When the signal is high state, then obviously the strength of that particular signal is strong 1. When the signal is in low state, then obviously the strength of that low signal is strong 0. Okay, so when the output changes from low to high, that means from 0 to 1, it has a delay time of delay R. Obviously, if this is our case that we are considering, this is a rise time, isn't it? This is a fall time. So when the control signal is from 0 to 1, what happens? The delay, the time rises from 0 to 90%. That means from 0, it's totally rising. So my delay would be with respect to rise time. So I can represent my delay with respect to delay underscore R. And when the control signal is going from 1 to 0, obviously it's falling down. So I can represent my delays with respect to fall time. Delay underscore F. So when the output changes from high to low, the delay is F. That is what this is about. TR, that is delay R, and TF, that is delay F. When it is going from 1 to 0, the delay F fall time. When it goes from 0 to 1, it is rise time, delay rise. Then the output turns off, it has a turn off delay. The time of delay is 0. So here, as we have three times, rise time, fall time, and turn off time. So here, turn off time says we represent the delay with respect to the turn off time, that is delay O. So when the output turns off, when the output turns off, we represent the time. The specified delay with respect to the turn off time is delay O. So R, NMOS, resistive NMOS, PMOS, and resistive PMOS switches to these three switches can be instantiated in the general form with respect to the same manner. Okay, that means what? As these are bidirectional gates, we can represent these gates with delays. We can represent similarly with delay 1 or 0. Delay 1 followed with the gate and the terminal list. Okay, if it is NMOS. This is with respect to delay. If there is no delay, simply tran terminal list. This is with respect to no delay. Okay, and if you want to represent with respect to the signal strength and the delays as well. Okay, in the bidirectional gates or switches, there is a time where you must represent the signal strength. Okay, then in such cases, we can represent, for example, NMOS. This is strong 0, strong 1. These are the strengths, and then follows with the delay rise, delay F. These are nothing but the delays, and then follows with the gate and then the terminal list. So with respect to the instantiation, with respect to the strengths and delays, this is how we represent. With respect to the delays, only with the delays, we can represent like this. Instantiation takes place, and with there is no delay. Okay, there is no delay. If there is no delay, it means what? The rise and fall times, both the switch on and switch off times are in the idle state. Okay, when the switch on and switch off times, they both are in the idle state. Remember, then the time is, the delay is 0. So in such cases, without delays, simply we can represent by considering the keyword and then followed with the terminal list. Okay, so this is what all about the bidirectional gates. So in the bidirectional gates, we have discussed about the different types of bidirectional gates. We have 6 types of bidirectional gates: tran, rtran, tran if 1, rtran if 1, tran if 0, and rtran if 0. So when it comes to normal gates with respect to the resistive switches, resistive bidirectional gates, the only similarity is, only difference is resistive switches. Okay, but the mechanism, when it comes to the mechanism, both the switches, both the gates are they switch on or else they goes, the functionality of both the gates are similar. Okay, when it comes to the instantiation, sometimes what happens in the switching process, we see there are some delays. Okay, we see there are sometimes no delays. No delays we see, sometimes we see delays, and there is a possibility of instantiating the signal strengths as well. Okay, when it comes to instantiate the signal strength, or else when it comes to instantiate the delays, the only thing we have to do is just represent in the starting itself. So if it is a signal strength, this is how we will represent. And also if there is a delays, this is what we have to represent. So when you are considering the strengths and the delays, sometimes what happens, a signal cannot propagate. That means what? Here the switch on and switch on time, off and on times, they both are in idle condition. When both are in idle condition, what happens? The delays is zero. The delays become zero. But when it comes to the instantiation, in the instantiation, you have to instantiate the strength. There is no need to instantiate the delays, because here the signal, the delay is zero, right? So there is no need to instantiate the delays. Rather, if there are delays, then you can instantiate the delay. So similarly, this is for NMOS, and we can go with the PMOS, RPMOS, CMOS, RCMOS as well. Why? Because they even are the bidirectional gates also. So this is all about the bidirectional gates. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.